Right now, somewhere, a copy of your data is sitting on a server that isn't yours, encrypted, scrambled, unreadable, and someone is keeping it anyway. Not because they can open it, because they're betting that soon something will. Intelligence agencies have a name for this strategy: harvest now, decrypt later. The machine they're all waiting for doesn't fully exist yet, but in labs on 3 continents, it's being born. This is the story of the impossible computer and the strange alliance with AI that's racing to finish it. Every computer you have ever touched speaks exactly one language: bits. A bit is a switch, on or off, 1 or 0. Your phone is a few billion of these switches, flipping very, very fast. A quantum bit, a qubit, breaks the rule that made computing make sense. Until the moment you measure it, a qubit isn't 1 or 0. It's a precise blend of both at once. Physicists call it superposition, and qubits can be linked, entangled, so that touching one instantly shapes its partner. Einstein hated this idea so much he called it spooky action at a distance. Experiments keep proving it real. Here's why that matters. Every qubit you add doesn't add capacity, it doubles it. 10 qubits hold about 1,000 states at once, 50 a quadrillion. 300 qubits can hold more states than there are atoms in the known universe. That's the promise. Now the catch. A qubit is the most fragile object humans have ever engineered. A stray vibration, a whisper of heat, a single cosmic ray, any of it collapses the magic mid-calculation. So we lock them inside this, a dilution refrigerator, colder than deep space. And even then, a qubit holds its thought for about 100 millionths of a second. For 30 years, critics said the noise would always win, that adding more qubits just adds more chaos. Then, in late 2024, Google's Willow chip did the thing 3 decades of theory had only promised. They scaled the error-corrected grid up, and the errors went down. Each time they grew it, errors halved. Google's benchmark claim: a 5-minute task that would take a classical supercomputer 10 septillion years. A contrived task, yes, but the error correction result underneath it changed the timeline for everything in this video. So what is this fragile frozen machine actually for? Not spreadsheets, not email. Nature itself runs on quantum mechanics. Every molecule, every protein, every battery chemistry. Classical computers choke on simulating that. A quantum computer doesn't imitate nature's math, it speaks it natively. But before quantum computers could compute much of anything, quantum physics found another job: keeping secrets. Remember, measuring a quantum state disturbs it, which means if you encode a message in quantum states, an eavesdropper can't listen quietly. The act of spying leaves fingerprints in the physics. That's quantum key distribution. Security enforced not by clever math, but by the laws of the universe. China took this out of the lab. In 2016, it launched Mischius, the world's first quantum satellite, beaming entangled photons between ground stations 1,000 kilometers apart. Today, China operates a quantum-secured network of over 12,000 kilometers of fiber, 145 nodes, 80 cities, banks, government agencies, power grids. Mischius has since burned up in the atmosphere. Its replacements are the size of a shoebox. Keep this network in mind. It's the answer to a question we haven't asked yet. Meanwhile, in the loud, hot world of classical computing, artificial intelligence was hitting a wall. Training a frontier AI model now takes clusters of over 100,000 GPUs. The newest AI campuses are being built to draw a gigawatt, the power demand of a major city for one computer. And the physics is closing in. For decades, chips got faster and cooler for free. That era is over. There's even a flow built into the universe. Landa's principle. Every time a chip erases a bit, which classical logic does constantly, physics demands a minimum toll paid in heat. Quantum logic is different. It's reversible. In theory, nothing is erased, so the toll never comes due. Now, in practice, quantum computers pay their bill elsewhere. That giant fridge draws about 25 kilowatts around the clock. That's roughly 10 air conditioners. A frontier AI campus draws 40,000 times more. So the obvious question, why not just run AI on the cold machine? Because the machine that might rescue AI currently can't survive without it. Here's the twist that never makes the headlines. Today, the most valuable thing happening between AI and quantum isn't quantum helping AI. It's AI keeping quantum computers alive. A quantum gate, the basic operation, isn't a switch. It's a physical event, a microwave pulse sculpted into a precise shape, fired down into the fridge to nudge a qubit. Get the shape slightly wrong, and the computation quietly rots. And every chip is different. Its own defects, its own crosstalk, its own personality. Worse, it drifts. A perfectly tuned quantum chip goes out of tune in hours, like a guitar that can hear the weather. Humans used to retune these machines by hand. Now, a reinforcement learning agent does it. The same family of AI that mastered Go. The agent designs a pulse, fires it, measures how badly it failed, designs a better one. Thousands of rounds later, it has learned that specific chip's noise fingerprint and how to cancel it. The results are not subtle, up to 10 times fewer errors than the manufacturer's own settings, and a calibration that used to survive 24 hours, the AI's version held for 25 days. There's a second trick. Another neural network studies the chip's outputs and learns its specific pattern of lies, then subtracts those lies from the answer. Several-fold cleaner results on the same noisy hardware. Before a quantum computer can think, AI has to teach it to hold a thought. So what happens when the two actually compute together? Not what you'd expect. Nobody runs a whole AI on a quantum chip. Instead, the GPU does what it's good at and hands the one impossible step to the quantum processor, a coprocessor, like a graphics card for reality's own math. There's even an elegant hack for training it. You can't peek inside a quantum computer without destroying the computation. So how do you get a learning signal out? You run the circuit twice, once nudged forward, once nudged back. The difference between the two answers is your gradient. The quantum chip slots straight into the same training loop as any neural network. And this is already producing results. Researchers took a standard satellite vision AI, ripped out its deepest layer, and replaced it with a small quantum circuit. The hybrid beat the classical version at mapping the Earth. The bigger prizes are lined up behind it. Drug and materials discovery, because electrons are quantum objects and simulating them on a quantum machine is home field advantage. Logistics, where in early tests, the quantum subroutine's runtime stays nearly flat while the problem around it explodes. But two brutal problems still gate all of it. First, sometimes quantum AI simply cannot learn. Scale the system up and the training landscape goes exponentially flat, a desert with no slope, no signal, no direction. Researchers call them barren plateaus. The optimizer just wanders. Second, And this one is embarrassing. The doorway. Getting ordinary data into a quantum state can cost more than the quantum speedup is worth. In a recent quantum memory experiment, 4-bit data loaded at 81% fidelity, 8-bit 60. The hallway to the miracle machine is where the miracle dies. Neither problem is solved, but both are being engineered around. Smarter training maps, special purpose quantum memory. This is what a technology looks like mid-birth. All of this, the fridges, the AI babysitters, the hybrid chips, used to belong to 3 or 4 countries. In 2023, India decided to join with the National Quantum Mission. 6,000 crore rupees to build a sovereign quantum ecosystem. Machines, networks, sensors, startups. It's moving. QSIM, a homegrown simulator on the Param supercomputers, lets Indian researchers rehearse quantum algorithms without touching scarce hardware. 8 startups now build the unglamorous essentials: cryogenic cables, atomic clocks, single photon detectors. And in Bengaluru this year, QPI AI unveiled Kaveri, a 64-qubit superconducting processor. Only a handful of countries can design and fabricate a chip like this. India just became one of them. But the sharpest detail is hidden in the timing. A Kaveri qubit holds its state for about 100 microseconds. Standard software error checking takes 60 of those. Most of the qubit's lifetime gone. So QPI AI built the error checker into hardware. It answers in 1.5 microseconds. Classical intelligence, guarding quantum fragility. The exact story of this whole video, engineered in Bengaluru. Next on India's roadmap, satellite quantum links spanning 2,000 kilometers. The same Unbreakable Network playbook China has been running for a decade. Which brings us back to the beginning. Why would anyone hoard data they cannot read? In 1994, mathematician Peter Shor proved something chilling. A sufficiently large quantum computer could factor huge numbers exponentially faster than any classical machine. That sounds academic. It isn't. Nearly every lock on the digital world, your bank login, your messages, government secrets, rests on one assumption: that multiplying 2 giant primes is easy, but unmultiplying them is practically impossible. Shor's algorithm deletes that assumption. All that's missing is the machine. Security researchers call the arrival date Q-Day. Current estimates cluster between 2029 and 2033. This March, Google's own security team warned it could be as early as 2029. The defense exists. New quantum-proof encryption was standardized in 2024. The old locks are scheduled for retirement by 2030 and banned by 2035. But as of this year, only about 13% of organizations have actually made the switch. The global bill for changing every lock, an estimated $15 billion, and rising the longer everyone waits. Now the cold open makes sense. Anything stolen today that must stay secret for a decade, medical records, financial archives, state secrets, is already living on borrowed time. And the counterweight? You've already seen it. Physics-secured networks. 12,000 kilometers of it in China. 2,000 more planned over India. The same science that breaks the locks builds the ones that can't be broken. So where does this actually land? Be clear about what quantum computing is not. It will not replace your laptop. It is not a faster computer. It's a different one. Brilliant at a narrow set of problems and useless at almost everything else. The honest scorecard right now? Error correction, finally working and improving as machines grow. Roadmaps at IBM and Google now put large, fault-tolerant machines around the end of this decade. The AI partnership, already real, already shipping on both sides of the fridge. And a warning label. Anyone selling you a quantum trading bot or a quantum health bracelet today is selling you noise. The real thing is rarer, colder, and stranger. The last time physics and computing collided like this, the result was the transistor, and from it, the entire modern world. This collision is bigger. The question is no longer whether the impossible machine arrives. It's whether we change the locks before it does.